Okay.
It's been forever since we had a class. I think we were talking about Venn diagrams last time. So, that being said, let's figure something out. We're going to use this later in a couple of classes. The magnitude of the union of two sets. I want that in terms of the sizes of the individual sets in the union. What would you be able to tell me about that? Well, you can use a Venn diagram to illustrate the idea. So let's say I just want generally, so remember we try to overlap things. So A union B, what does A union B look like? Well, take all of A, and you take all of B, union. Anything that's in A or B. Now based on that picture that we just drew, what do you think this is going to be? The size of the set A union B. Yeah?
Like the magnitude of A plus the magnitude of B minus the magnitude of the intersection.
Right, because the intersection you'll notice is shaded twice, and sets only count things once. So by counting A and B, we're potentially double counting anything that's in their intersection, and so we have to subtract the size of the intersection. And that's an important equation. We are going to use it at some point in 2 or 3 classes. It's called the Inclusion-Exclusion principle. You can extend it to multiple sets, but this is the one for 2 sets. The other one, you'd add all the magnitudes of each individual set, subtract all the intersections, then add all the triple intersections, and subtract all the quadruple intersections, and so on and so forth. But yeah, very important equation. We're going to make use of that. Just wanted to make sure I told you guys. I don't think I told you guys that. So the inclusion-exclusion principle, very important. Now, the next phase of the class, to celebrate our time back, we have an activity that I want to do that I did with the other class. So we're going to run through this. So the next phase is we're going into probability. This is I'm going to start by having a little fun with it. We're just going to jump in without knowing too much about probability, see how we do. Yeah. How many? How many are missing?
Because I didn't know how they sized for all the dice.
Cheers. So this is what we're gonna do. I want to see where you guys are with probability. We're gonna have a little fun with this. I'm gonna have fun. I don't know if you guys want to do that. I'm gonna have fun. You guys can join me. So we want to start the section on probability teasers. Maybe a little bit of background so that it's not completely unfair. How many people have taken probability before? Yes, we get another paper. 2?
Yeah.
How many people have taken probability before? Okay, a little more than a handful. How many of you watch this when you do this activity with the other class on the video? You actually watch it? Okay, so you have to be quiet. I'm surprised. I don't know. Like people who watch the class and then attend the class, putting in the extra effort. That's what I like to see. Okay. So, you're not allowed to answer anything. So this is for the rest of you. Maybe the people who haven't done probability before as well, just to make it a little bit more interesting, a little bit more fun. Let's talk about a fuzzy definition of probability. We'll make it more precise later on. What is a probability? So let A be some event, right? Something that's going to occur. What is the probability of A? And we denote this by P of A. The probability of A. It's not the fancy P like for power set. What would you say a probability is? How would you describe it definition-wise? Yeah.
Chance that something will happen.
Chances that A would happen? That A happens. Be a little bit more precise. Make that a little bit more mathematical. How do we get numbers in here? Yeah? Yes? Yeah?
The chance as a percentage out of 100 that if that happens.
Yeah, sure. As a percentage, how would you go about finding that percentage? How do you go about finding the percentage? Yeah.
The number of outcomes of A divided by the number of total outcomes possible.
Right. This is basically what it is. It's going to be a ratio. Basically, you're going to figure out the number of ways A can happen. And you're going to divide by the total number of possibilities. So probability, you can think of it as a measure of chances or likelihood, or a nice way to think of it, at least finite probabilities, is just a measure of relative frequency. Roughly how often you expect something to happen. It's also important that you realize that this is on the aggregate. What is that? What is that? Do I mean by that? Okay, so let's give a very simple example. The coin toss. Very simple example. Not easy to say it, obviously. So you have a coin. One side is heads, one side is tails. Flip the coin, and like you don't know what it's going to land on. There are some chances that it would land with heads facing up. We say it lands on heads, or that the tails would be facing up, which is the other side. And how would we talk about the probability of getting heads when you flip a coin? Well, you would talk about the total number of possibilities that can happen when you flip a coin. There would be two of them. You can get either heads or tails. So if my A is the event of getting a heads, I would say the probability of that event is the number of ways that that can happen, which is there's only one way. It has to land with the heads facing up, divided by the total number of possibilities, which there are two ways. So the probability of getting heads on a single coin toss is going to be 1 out of 2, 1/2, or 50%. Now that does not mean exactly 50% of the time that you flip a coin you'll get heads. However, it means on the aggregate. If you were to flip a coin thousands of times, millions of times, then the number of times you'll hit heads is going to be roughly 50%. You will get closer and closer to 50% the more and the more you do it. Okay? So you can flip a coin twice and you get tails both times. It doesn't mean like there's 100% failure here. It just means you haven't actually tried something enough. That's gonna be important. But that we'll get into later. But this is the basic idea behind the probability. Kind of measuring the chances of something happen as a percentage, and you're pretty much considering this kind of ratio. Okay, that's it. Now, that being said, let's look at some problems. So this is the idea that we're going to apply to all these problems. And let's start with problem 1. Very famous problem. It's called the Monty Hall problem. that's problem one in our probability teasers. So here's the situation. Now this was back in the day, was a very famous problem, came out in magazines in the 70s or so, back when everyone used to read magazines and talk about it. The problem goes like this. You're on a game show, okay? It's kind of like, there has been a more recent show with like Wayne Brady. What is that called again? The one with the songs? Let's Make a Deal. It's pretty much like that. So you're on a game show and there are 3 doors. Okay, now behind one door is a car. Behind the other 2, some lesser prizes. Traditionally, goats. But at least in the original version, that's what was said. Okay, so there's a car behind one of these doors. And behind the other 2 doors, there are goats. So you're a contestant on this game show. Monty Hall is the host of the game show. So he comes out and says, okay, you know what? You can pick any door you want, and we will give you the prize that is behind that door. So, pick a door, pick a door. Door number 1. Everyone picks door number 1. You're always going to be lucky number 1. Okay, door number 1. And so Monty Hall says, okay, I'll tell you what. I'm going to actually show you what's behind door number 3. He opens door number 3. And there's a goat behind door number 3. Hey, what if yours is a goat? You know what? You seem like a good guy, and I'm going to give you a chance to walk away with something here. I'm going to give you a chance to switch your answer. Do you want to change from your door number 1 to door number 2? Because, I mean, there could be a goat here. There was a goat up there. Do you want to switch?
No.
So that's the question. That is the big question of the Monty Hall problem. Should you switch? What do you guys think? Yeah?
I think no, because why would he show you the goat if he doesn't want you to switch your answer so you can keep the car?
Oh, you think the game host is trying to play mind games with you? That's
Yeah.
your.
That's the
Yeah,
whole
he's
point.
playing mind games.
Yeah.
How do you know he wouldn't have shown you the other one anyway? Just to keep the suspense up for the audience.
But they're all goats.
They're all good. Yeah, that could be the case, but I mean, come on. Let's see. Okay. All right. Yes. No. Show of hands. Yes.
Yes.
Wait, are you saying
Wait,
yes?
yes to change.
Yes to switch. Yes or no to switching. You'd switch because you don't trust the guy?
No.
There's another reason? Okay. So 1, 2, 3, 4, 5, 6, 7, 8. We're jumping on the bandwagon here. Okay, 8 people would say they would switch. How many? No, it doesn't make a difference. The door, what's behind the doors hasn't changed. Doesn't make a difference. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah, I mean, it makes a lot of sense for you to not switch. That's the wrong answer, though. Switching is the better strategy. Let's move on to the next problem. So, the better thing to do would be to switch. You would win the car more often by switching. Okay, so probably the teaser. I'm not really going to tell you the answer right now. We're going to leave the suspense. Let's move on to the next one.
Suspense is killing me.
And it doesn't have to do with thinking the host is playing mind games on you or anything. No, straight up by the numbers, it is better to switch. The probability of you winning the car is higher if you switch the doors. Let's look at the other problem. Now, the problems on the first page, these are all equivalent. The solutions to them would be exactly the same, mathematically speaking. I just thought I'd tell you the many ways that this problem has been posed. Another very famous variation. 3 is not that popular, but another very famous variation of the Monty Hall problem is the 3 prisoners problem. Okay? So the situation is this: you have 3 prisoners, they're on death row. Let's call it prisoner A, B, and C. Right? They're on death row. Now, the governor is instituting this new initiative, you know, we're killing too many inmates, so one will randomly be set free. At least randomly according to the prisoners. Maybe the people in charge actually know who's going to be set free. Now, here's the situation. So you have all these 3 people on death row, and they come and they announce to them, you know what? We're letting one of you guys go. We're not going to tell you who, but one of you will be let free. The other 2 of you, we're going to execute you by the end of this week. Right? So you can imagine these guys are not in good shape, right? They can't sleep well, blah, blah, blah. Okay, so prisoner A goes to the warden. And he says, please, I'm a mess here. I can't sleep. You know, there's a 1 in 3 chance that I'm going to die at the end of this week. Just, come on, give me something. Just tell me something. I know you can't tell me who's going to be let free because you're probably afraid of retaliation. Okay, so you don't have to tell me who's going to be set free. Just at least tell me, am I going to be one of the ones who are going to die? The warden says to him, well, I'm not going to tell you who's going to be set free. I'm not going to tell you about your own fate, but I'm going to tell you B is going to die. So the warden tells him, one of the people that's going to die is prisoner B. Right? Let me be a little bit more suggestive, because last time I opened door C, so let's say he says, you know what, prisoner C is going to die. That's the goat. Now, this guy feels relieved, because before, he had a 1 in 3 chance of dying. His chances of 1 in 3 chances of living, he had a 33% chance of living, but now we know this guy's gonna die, so he has a 50% chance of living, right? It actually doesn't matter which one of these prisoners you are if it's going to be random, right? So, okay, he feels good. His chances have actually gone up. Here's the thing though. After hearing the news, it turns out that A's chances has not changed. It turns out, probabilistically speaking, he still has a 33% chances of dying. And B's chances of living doubled. Let's move on to the next problem. The guy who asked the question, his chances haven't changed. However, it's more likely that the other guy is going to live. It's more likely that the other door has the car. By the numbers. Now, it's not like a mind game, anything. It's just by the numbers. There are 3 possibilities of one of these people are going to live. If you know one of the people are going to die, does it make the possibilities of the other 2 50-50? Turns out it doesn't. It actually makes one of them 2/3 and the other one 1/3. So yeah, let's move on. Think about it. Think about it. If you think about it, just maybe draw out some pictures, draw out some situations. This one's probably a little bit easier to digest. Let's look at problem 4. The 2 children problem. A couple has 2 children. Okay, so here are the questions. A, what is the probability that both are girls? So assume the probability of being born a boy or a girl is straight up 50-50. It's dead even, right? Assuming that, right? Assume probability of having a boy is a half, and the probability of having a girl is a half. You know a couple has 2 children. Note they didn't tell you what the sex of those children were. If someone asks you, if you were to bet that both were girls, what are the chances that you would be right? What do you think? Yep, Christian.
It'd be like 1/4.
1/4. How do you get that?
Because probability of one child being a girl is 1/2, so you multiply 1/2 by 1/2.
Why did you multiply?
Oh, multiply because it's the probability of, like if you, I'm not sure how to explain it, just thought
You
that was normal.
just multiply just because you feel like it?
No, not because I felt like it, I just thought that.
You know this is what you should do.
Yeah, I know that's what I should do, I just don't know what.
Okay. You had a different answer?
No, it's
1/4? Okay. We'll see why it's 1/4. Why does it make sense to multiply a half and a half? Why didn't we do something else with them? Okay, so here is the second situation. So you're told one is a girl. What is the probability they're both girls? Probably if you have 2 girls is a 1/4. I tell you that one of them is a girl. What's the probability that both of them are girls? Yeah.
50%. So you already have one of them, so you're just asking.
Yeah, so you're just asking about the other girl, right? You know one is a girl, so the probability of being a boy or a girl is a half. So you just focus on the other one. Makes a lot of sense. The answer is a 1/3. Let's move on. Okay, listen carefully now. You're told the older is a girl. This is an important part of the clue. Her name is Freuda. What is the probability both are girls? Isn't that kind of the same thing? Isn't it also a 1/3? Wait, why was it a 1/3 in the first place? Who the hell knows that? Like, why is it a 1/3? What do you think this one is?
It's
Because you said older.
1%. He's going on, yeah. It is a half. It's a half. That one's a half. Let's do another one. Okay, now we have that. Let's do, what did I say in this version? You know, one child is a girl, and listen, she's born on a Monday. Probability, both are girls. Yeah.
I'm gonna guess a half,
Why would you guess that happened?
because it kind of seems like the girls being qualified or something, like her being born on Monday, like she's having.
Oh yeah, you think like, okay, the fact that I actually told you some information about one of the girls kind of make it, these two are actually the same thing. Yeah.
I haven't seen this one.
Okay.
I think it's still a 1/3. He doesn't see. You say that it's the older child that's saying Florida, whereas as in B and in the case of D and D, you don't say which girl is which.
Yeah.
I think that would be the same.
Oh, so you think it goes back to a 1/3?
I think because he said older, that's obvious.
Yeah, I just said one of the girls born on a Monday. Yeah. I didn't say it was the older girl that was born on a Monday. Yeah, that's true. 13/27 is the answer.
Yeah, it was closer.
he was closer. But this isn't like The Price is Right. This is, the game show problems are done. Yeah, okay. Okay, let's look at another problem. Let's see what the intuition is. Maybe you'll have more luck with this one. I'm having fun. I'm having fun. 5. You have 4 cards. Two black, 2 red. You shuffle. Pick 2 randomly. What is the probability that you get both the same color? One what? 160.
I think it's a half, 1/6.
Oh wait, never mind. What was
Is that because you're doing the 1/4 times the 1/4? Is that how you're getting
Oh, wait, no,
160?
there's removal. Oh.
Huh?
So there's no replacement, so you have to adjust for that. So
Yeah, I'm picking in both of
How
them.
many
Yeah, yeah. You put 4 cards on the table, I randomly draw 2 minus. Yeah.
third?
1/3. Why?
Because when you take out the first one, there's now one of the same out of 3 remaining.
He's actually right. It's 1/3. We'll get back to his sort of reasoning. Let's see if it actually holds water later. Okay. Similar. 4 coins this time. Toss. Okay. Take 4 coins. Throw them on a table. Probability to show heads. Yeah, think about that. Well, it's kind of like 4 cards. You know, you have red and black, heads or tails. What do you think? Huh? A half. Yeah. Yeah, a half. So 3 8s is the answer. Okay. Birthday problem. Very famous problem. We're gonna learn how to solve all these problems, by the way, so don't worry. It's like, man, probability's hard. It's like, we don't know how to set it up yet. I'm just seeing where your intuition is. 7 is the birthday problem. Now this one, even if you know how to do it, coming up with the number off the top of your head is going to be challenging. Or maybe you can actually just tell me the expression that would give you the answer. That could work out. But how many people must be in a room so that it's likely means there's more than a 50% chance at least 2 have the same birthday. This is called the birthday problem. Can you guess roughly what that would be? No clue. Some ideas. Yeah?
Is it 365 choose 2?
365 choose 2. Well, I don't think so. That's gonna be way too big. It's actually around 23. Chances are someone in this room has your birthday, believe it or not. We have more than 23 students. I don't know, should we try it? Okay, go, quick.
February 1st.
Yeah.
October 21st.
Today.
Yes?
That's
No.
No.
Oh! I was so confident. Happy birthday! Like, this is my gift to you. Okay. Yeah, that is today. I didn't know. I thought we had a map. I was so excited. Tomorrow's my dad. Any June 7s?
December 22nd.
March 1st.
March 1st.
Yeah, the chances were more than 50%. Like every 2 times I do that in a group of more than 23 people, on average, I would actually get a hit. Yeah, we didn't even get through the whole class. Yeah, that's you don't need that many people. You'd be surprised. You think there's 365 days in a year. Don't I need a lot of people to match up on birthdays? No, you need 23.
Why?
Why? Why is the question? That is a good question. Why? Why 23? Okay, at a certain intersection, every minute, 25 cars pass. Let's say you have a government job, you're doing a survey. You just stand there at an intersection and count how many cars pass every minute. You find that 25 cars pass on average every minute. Okay, so if someone just randomly comes and says, okay, start the clock now, and you run it for a minute, what are the chances that exactly 25 cars are going to pass in that particular minute? So this is the intersection problem. It's tough. We may or may not learn how to solve that problem, depends on how much time we have. You'll actually solve it using something called a Poisson random variable. It's actually
You say croissant?
No,
Poisson.
like the fish.
Yeah, it's spelled like this, but it's French, so you have to make it all
That's
fancy.
poison.
No, poisson. It's 2 S's. It's poisson. You have to say it. It's French. It's French. You have to say it fancy. You have to. Okay. That's 9%. Okay, so now 9, that's something that we are not going to be able to solve. I just threw that one there for fun. You actually need calculus to be able to solve that one. You need calculus-based probability, and we do not know calculus. So this is like, you know those romantic movies where it's like, you know, they meet just by happenstance, right? So this is actually looking at the chances of one of those romantic comedies actually happening, right? You have 2 people get to a train platform every day between 5 and 6 p.m. They'll stay for 5 minutes. What is the chances that on some day they're actually going to meet? They'll actually stumble into each other. And it turns out that the probability of that is 23 out of 144. 23, yeah. Okay. So we're all good with probability, right? Can you move on? We got it. Okay.
I think you go to the rest of
Poisson. Poisson. Okay. You have to say it like that. I feel like that was a good learning experience. Learning that we know nothing. You know nothing, Johnson. Okay. Too soon. I'm not over-seasoning. Okay. Let's, she's very, not ashamed to admit it. Let's actually look through some of these. Let's look back at the Monty Hall problem. It might have been strange to you. Why did it make sense to switch? How in the world would that make sense? It shouldn't change. The car and the goat didn't change positions. Why should my choice change positions? Let me reveal to you the answer by showing you 3 scenarios. Now, this isn't exhaustive, but by looking at this, you'll see why switching is actually better. So in 3 different scenarios, what I'm going to do is I'm going to show you what would happen if you switch versus you stay. What will happen in each situation? So, let's say okay, so check is your first choice. And C is the location of the car. Now the location of the car can be behind any one of these doors, but for the illustrative purposes, let's say it is behind door number 3 in this example. So that's where the car is, but we don't know. We don't know that, right? But it's behind 3. So I'm pulling back the curtains for you guys. You guys are the workers behind the scenes. Okay. Now, there are three possibilities for what you could pick when I gave you the choice, right? So I said, hey, what door would you like to open? You could say, I'd like door number 1, Monty, right? Or in another universe, your doppelganger could be saying like, door number 2, right? Or you could have said, door number 3, okay? Now, what's going to happen? The host is always going to try to play mind games with you. So when you pick door number 1, he knows door number 3 has the car, so what he's going to do is he's going to open door number 2.
You just said
He's
no
going to
mind
show
games.
you a goat. What?
You said no mind games.
Yeah, but let's even pretend that we throw that in there. It's not going to matter. The numbers are still going to work out. He's going to show you door number 2. There's a goat. Do you want to switch? Now, if your answer was yes, you would switch into door number 3. You would actually win the car. You would lose by staying put. It's not going to matter, Monty. I'll stick with my door. You'd lose. You didn't have to lose. What about if you were in this situation? I picked door number 2, Monty. Oh, look behind door number 1. There's a goat. Do you want to switch? Yes, I want to switch. I will take door number 3. What's going to happen? You are going to win. If you decide to stay, you would lose. Last scenario. Cars behind door number 3. I like door number 3, Monty. Look behind door number 1. There's a goat. Do you want to switch? I'll switch. This time you lose. If you had stayed, you would have won. But what do you notice here? By switching, you win 2 out of 3 times. The numbers are the numbers. You're twice as likely to win if you switch the doors. And it's not because of a feeling, it's because of, well, that's what the numbers say. Like, as a random game of chance, whether someone's messing with you or not, which you can't predict, you should switch doors. And this is the same reason why the other prisoner has 2/3 chance of surviving, while the guy who was separated had only 1/3 chance. So yeah, you should switch. That's the correct answer to the problem. And back when it was first introduced, it was a very controversial answer, but that's the answer to the Monty Hall problem. It's better to switch. So that's why it's better to switch. Now you know. Now what you can see, you're starting to see how we're going to be doing probability. You're going to want to be able to visualize the situation. Remember, it's always a ratio. What are all the total possibilities versus what the outcome I'm looking for? And you just need to find a very convenient way to chart that out. And of course, be able to count how many ways. So out of the 3 scenarios, 2 of them we won by switching. So the probability of winning by switching is 2/3. Let's look at the 2 girls problem. Let's look at that one. And I'm going to start that by figuring out how do we want to represent the children. This is going to be another popular way to do it. So sometimes you can draw a picture, you can draw a diagram. We're going to draw tree diagrams and all sorts of stuff like that moving forward. But sometimes you actually want to think in terms of mathematical objects like sets or tuples. There's a reason why we introduced those. Would you consider the children as being a set of children versus a tuple of children? Huh? Tuple makes more sense. Why? Because if I have a set and there are 2 girls in it, what's going to happen? The set ignores one of the possibilities. So you'd erase one of the children, like there's Thanos or something. That wouldn't be a good thing. It's better here to represent by tuples. So what you have now is you have the possibilities. You can have a girl first and a girl second. You could have a girl first and a boy second. You could have a boy first and a girl second. You could have 2 boys. So if you know a couple has 4 children, this is the possibilities for 4 children. In how many of those total possibilities do we have 2 girls? In one of them. 1 out of 4 times, they will have 2 girls. So that was actually how part A worked out. What about part B? What are the possibilities here? So reread the problem and see if you can figure it out. Yeah.
Just like the same things that we get with the two boys.
There's no 2 boys. In the other situation, we said, you now know one is a girl. One is definitely a girl. Which means boy, boy is no longer in the realm of possibilities. Right now, you have 3 chances. 3 possible scenarios. You know that one of them is a girl, which means there are only 3 possibilities. How many of those possibilities has 2 girls? Well, 1 out of the 3. So the probability here was 1/4. The probability here is 1/3. Okay? Why was the third one a half? Is it because the girl's name was Freuda? Yeah?
Because she's older, so you know that first child was a girl.
Right. We're told the older girl's name is Freuda. Her name actually doesn't really matter. The fact that she was the first child matters. The fact that the girl has to be in the first position means this is also now no longer a possibility. You now have 2 possibilities. If someone says the older child is a girl, there are only 2 ways for that to happen. And you have both girls in 1 out of 2 ways. So I want you to notice what's happening here. So let's look at a naive strategy, which we'll make clear later. We'll make more clear later. So you're faced with a random probability problem. Blah 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 blah. What's the probability of blah? Right? What is the strategy? How do you actually approach this problem? Well, one, you have to find a way to visualize the problem. Visualize, of course, here is in quotes. So sets, tuples, something else. Find a useful way to represent the problem in your head so you can see all the possibilities kind of laid out for you in some sort of strategic way, strategic, objective way. 2, you're going to want to be able to count the total possibilities. In the first situation, it was 4. In the second situation, it was 3. In the third situation, it was 2. This is going to give you the denominator of your probability. Then 3, you're going to want to count the number of ways what you want can happen. And then step 4, the probability is going to be equal to the answer in 3 divided by the answer in 2. This is a very naive way to look at a probability, at least the probability that we will be doing in this class, which is finite probability. There will only ever be finite number of things. But here's one thing that you should notice. Visualizing pretty important, but it's also pretty important that we know how to count. Because not always are we just going to be dealing with 4 possibilities. Sometimes we'll be dealing with thousands of possibilities. So we're going to need to be able to count things very efficiently, right? So a lot of people think they know how to count. So a lot of people think counting means 1, 2, 3, 4. But like I said, we're going to need to be able to do it much more efficiently. And by that I don't mean, I don't mean do it faster. I mean you want to be able to count without counting, without actually counting. How can you actually set up strategies for counting to large things, not making a mistake, just by figuring out a convenient way to visualize them? And this leads to us needing something called, well, we're not going to go very deep into it, but basic combinatorics. Combinatorics is a fancy word for counting. Counting without counting. When most people think counting, they actually think of something that's technically referred to as enumerating. Right? You going 1, 2, 3, 4, it's called enumeration. Right? We want to be able to count without enumerating. Now, sometimes enumerating is going to be the best way. Enumerating is in fact what we just did with this 2 girls problem. I literally counted each possibility one by one. It's not always going to be efficient. We are going to want to count, and we're going to want to be able to count a lot more efficiently. Because 2 out of 4 steps is going to require us to count stuff. So we need to have a way to visualize certain things and a way to count certain things. The visualization is going to happen a lot in terms of sets and tuples, sometimes tree diagrams, some other and tables that I'll be showing you guys how to construct. Sometimes in terms of Venn diagrams can be helpful in probability. We'll actually use Venn diagrams to derive some of the formulas for probability. But once you can visualize something, you're going to need a way to count them. And so that actually leads to counting. By the way, what about the last problem? The 2 girls. One born on a Monday. Tell me how you would visualize that. Yeah?
Do the same thing as step B, because the born on a Monday is irrelevant.
It's not irrelevant. So tuples make sense before, so it probably still makes sense now, except now we would need what we call a 4 tuple, if you want to represent it this way. And in fact, you could represent it with something like a matrix, a 2 by 2 matrix, but that's not even go there. It's too soon. But yeah, I could set up a 4 coordinate, right? Where I have something like sex of first child and day first child born and sex of second child and day second child born. Now you are told that one is born on a Monday, which means you would have 2 sets of situations to count. Either you would have dash m dash dash. You know that one is a girl born on a Monday. Or we have dash dash girl born on a Monday. And now you would have 2 other possibilities for here. Here you'd have G or B. And here you'd have G or B. Here you have 7 possibilities: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. And here you have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So we have 7 things that can be here, 2 things that can be here. What is the total number of possibilities here, would you say? Would you guess? If I can put 2 things here, and for each thing I put there, I can put 7 things here. Right, 14. Double them up, you get 28. You would notice that there's going to be 1 overlap whenever a GM shows up in that position. So that brings it down to 27 total possibilities, which is why the denominator of the answer was 27. So if you're wondering where did 27 come from, that's where it came from. The day of the week actually mattered here. Yes?
Why would you subtract one of those?
Because there would be an overlap. There's going to be a coordinate, in particular GM, that they're going to be the same. So we're not going to count that twice. Because the GM is going to be an overlap. So out of the 28, there's really only 27 I'm thinking about.
Why can't both be girls who are born?
Because you're in the situation where the first is a girl born on a Monday and the second is a girl born on a Monday. This it's saying exactly the same statement. Right. So you would throw away that one coordinate. So out of the 28 coordinates, only 27 of them represent distinct possibilities. And that's why the denominator is 27. And now you're going to go through and you're going to count how many of those coordinates have 2 G's in it. Now, that is automatically, right now, bigger than the 2 girls situation, right, where you had just 4 coordinates to count. Now you have 28. How do you know that you're counting without missing anything, right? What if you had even more than 28? Right? If you only knew that one was born on a Monday, you don't even know the sex, then you have even more, right? So the situation can get really big really fast, and you have to be very efficient at counting things like tuples, counting things like sets. And so that's where we're going to spend the next 2 or 3 classes. Focus on the counting part. How are we going to count various situations? What are the formulas? What are the strategies? What are the theorems? That's going to help us to count things very nicely. Then we're going to go back to probability, and I'm going to teach you how to visualize this. And now, once you have the counting under your belt and you know how to visualize things, going through these 4 steps is not going to be a big deal in general. So that's the goal. That's where we're going to go. And so let's get the train rolling. Let's start with counting. So, first principle I want to introduce. Let A be finite sets. Okay, so we have 2 sets with there's a finite number of things in each of them, right? So it's not an infinite set. We're in finite math. Okay. So then the number of tuples A comma B such that A comes from the first set and B comes from the second set that can be formed. Right, so if you have 2 sets, A and B, how many coordinates could you create from those sets? If you were to create all possible coordinates, where the first coordinate is someone that you randomly picked from A, and the second coordinate is someone you randomly picked from B, how many total possible coordinates are there? It turns out you will have the size of A times the size of B. That's how many total coordinates there will be. So, for example, we have, let's say A is the set 1, 2, B is the set A, B, C. How many ABs are there? Well, let's not mix these up. Plus X, Y, Z. How many ABs are there such that A is from A and B is from B? Well, in one situation, the A can be 1, and then the B has the option of being X, or Y, or Z, right? So once there's a 1 in the first position, there are 3 possibilities for the second position. But there's another possibility for the first position, right? It could be 2. And if the first position is 2, the second position could be an X, or it could be a Y, or it could be a Z. And that's all possibilities. Notice that there are 6 total possibilities. And I want you to notice that this is equal to the size of A times the size of B. It's 2 times 3. It's not a coincidence. So if I have 2 sets of a certain size, how many ways can I pair off the elements? Multiply the sizes. It's a very basic counting rule. This is called the multiplication rule. Now, there's a reason why I stated it in terms of tuples. It's not usually stated in terms of tuples, but being able to think about tuples is going to be a very important thing for us. So I also want you to know how the rule looks like in tuples. It is also commonly stated it's all commonly expanded. Because this can work for more than 2 sets. You could have 3 coordinates, 4 coordinates, and you just keep multiplying. It's normally expanded and stated as. So if you've seen probability in high school, chances are this is how they told you the multiplication rule was. If you have an experiment with m stages, right? So something is happening in m stages, right? And the number of possible outcomes for first stage is, say, m1. Number of possible outcomes for second stage is n2, ... Number of the mth stage is n sub m. Then total possible outcomes for the whole experiment is going to be equal to the multiplication of all of these guys, n1 times n2 times ... n. Think of the coin problem that we had earlier as well. 4 coins randomly tossed on a table. You can think of the 4 coins as 4 stages in an experiment. Think of each coin as a stage. Number of possibilities for one coin is 2. For the other one is 2. For the other one is 2. You could actually count, if you wanted to count the coins in order, you could actually multiply 2 by 2 by 2 by 2 and use that as the total possible outcomes. And then you can count, we'll do it that way. But this is called the multiplication rule. Figure out how many ways each stage of an experiment can happen. The outcome of the entire experiment from start to end is going to be the product of all those numbers. That's called the multiplication rule. Silly example. Suppose a phone number is 10 digits long and must start with a 1, no restriction otherwise. How many phone numbers are there? Again, you can apply a multiplication rule. Think of each digit as a stage in the experiment. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stages to the experiment. And there's only one way for the first stage to occur. How many ways can the second stage occur? 10. There are 10 digits from 0 through 9. So there are 10 ways for this to occur, 10 ways for that to occur, 10 ways. There's no restriction otherwise. 10, 10. Total number of possibilities. Well, according to the multiplication rule, it's going to be 10 times 10 times 10 times 10, 10 to the 9th. There are a billion possibilities for such a phone number. Are you going to sit down and count to a billion? Probably not. If you counted one number every second, how long would it take you to count to a billion? You guys know?
Be
Huh?
be dead.
You wouldn't, you know, you wouldn't be dead.
It took like 30 years or something like that. I think I've seen this one.
Yeah. To count to 1 million takes 11 days of non-stop counting, one number every second. Count to 1 billion, 32 years. So if you guys started counting since you were born, you wouldn't have made 1 billion yet. You're not going to do it by the end of an exam. You need to know the multiplication. How many possible phone numbers? Here's one possibility. Here's another one. Like, you're not going to, yeah, it's not going to happen. So if I ask you a question, what is the probability that the first 3 digits of someone's phone number is 1129? Are you going to find that probability? Let's count the total number of possibilities. Yeah. No, it's not going to. It's not going to work. No, you're going to use the multiplication. Okay. What is the probability that my stalker is going to figure out my phone number if he knows the first 4 digits? What is the chances I'm safe? Got to real. Okay. So multiplication rule. First rule. Here's another one. Let A be a set with the size of A is n. So here's a set with n elements. N is a natural number. Now, how many m tuples can be formed where m is less than or equal to n without restriction? Now, an m tuple is just a coordinate with m slots, dot, dot, dot. So tuple with n entries. Okay. So I can put anyone from A in here, put anyone else from A here, anyone else here, anyone else here, and continue up to m times. How many total number do I have? Well, the total number by the multiplication rule is going to be, you're going to multiply all the possibilities. Now, how many possibilities do you have for the first digit? Well, there are n possibilities, because there are n things. And there's no restriction, so I can choose any one of the guys again. I can choose any one of the guys again, right? So then it's going to be n times itself, m times. We're going to end up with n to the m total possible coordinates.
The actual number is infinite.
Oh, it's only infinite if the set itself is infinite.
Infinite.
And we're spending too much time together. You're starting to get cheesy jokes like that. Okay, so here's an important restriction. Very often, we're not going to want repeats. No repeats. How many coordinates? Okay. Same situation. I have a set with n elements. I'm going to pick a random person out of that and put it into a coordinate. But once I choose someone, I can't choose them again. I'm not allowed to repeat. So this one, no restriction. You can repeat if you want. There will be n to the m, an infinite. I'm gonna get in trouble by saying, well, did you say Jhevon said it was infinite? Like, what? Okay, so we have again m coordinates. How many number of ways for first choice? Okay. I can choose any of the n things. How many things can I choose here? n minus 1, because once I made the choice here, I can't pick that guy again, I have one less choice to make. Similarly, n minus 2. Similarly, n minus 3, dot, dot, dot. What's the last one? N minus m, people always forget the plus 1, right? You can think of this as n minus 0, 1, 2, 3. It'll actually count up to n when you end that. So this will actually be equal to, so the total number of m tuples without repeats is going to be equal to n times n minus 1 times n minus 2 all the way out to n minus n plus 1. This is a very important number. It shows up a lot. We give it a name. Does anyone remember what this is called? It is called P of n. It is called a permutation. Permutation of m objects from n objects. I'll tell you why the name permutation comes from next time. So we have something called a permutation. It is this expression. It's a very important expression. We came up with a name specifically for this expression. Why is it called a permutation? We will reveal next time. Next time we'll see why it's called that by considering P of n comma n. And it'll be clear why it's called a permutation. We'll stop there. We'll pick up on it first.
Oh, so if you're better.